Hello, I'm Julia. I'm on the science team here at GLE, and I'm here to talk about how the capacitive sensor works. So our capacitive sensor is an interdigitated capacitive sensor, which basically means its traces are interlocked, like when you clasp your fingers together. And what it does is it determines the dielectric constant of anything it's in contact with. So for our mission case, that would be determining the dielectric constant of the regolith on the moon. Now we'll talk about what all that means. So basically, we got to go over capacitors first before we can talk about our capacitive sensor. And a capacitor, in a very simple sense, is just two electrically charged plates next to each other with something in between. And that something in between is called a dielectric medium. What happens when we put charges on the capacitor plates is an electric field is generated between them. Now, that electric field polarizes the medium that's in between them, which basically means it sucks the charges pretty much closer to the plates. As you can see in the picture there, they get elongated and the charges attract to their opposite counterparts. And so basically the dielectric medium can have a different level of polarity, which basically determines how much it will stretch out, so to speak, and how separate those charges will get. So more polarization gets a larger capacitance, and that is just the ability to store energy in an electric field. So a more polarized substance in between, a more polarized dielectric, will store more energy in the same dielectric or in the same electric field when you charge a capacitor. So that's how what we're measuring is how dielectric, how polarizable maybe is the substance that's touching our dielectric sensor. So, for example, water is a very polar substance. Its charges separate pretty easily. And so that has a high dielectric constant, which is directly related to capacitance. So it has a higher capacitance and a greater ability to store energy in that electric field between two plates. That means since it has a larger capacitance and a higher energy cap, that means it takes a long time to discharge and charge up, i.e. it takes a while to store energy into that field because there's a lot of potential to store. Now, dry soil, for example, that doesn't polarize very well. So it has a low dielectric, a small capacitance, and that means it does not take very long to charge up because it has such a low potential to store energy in that electric field. That means when you put charges on those plates, it takes really quickly for those charges to polarize and get into their maximum energy state. So for a simpler example, you can just imagine water. So water we'll use as our analogy for electric charge, and we'll use buckets for capacitors. So you can imagine two buckets. One is super small, maybe a little glass, and then one is like a big old bucket. And we're filling them with water at a constant rate for both of them. The small glass is going to fill up super quickly versus the big bucket is going to take a long time to fill all the way up. So this is basically how capacitors work with different dielectric mediums in between them. So with something with a very polar or a very high dielectric constant in between the capacitor plates, it will act like a big bucket. So when we pour water into it, which is just putting an electric field across the capacitor, that will take a long time to fill up and store energy, or a long time to fill up with water. The small glass doesn't have a lot of potential to store energy, i.e. it doesn't have a lot of potential to store water, it has a small capacity, and so that will fill up a lot quicker. So basically, what this is all saying is that charge and discharge time is directly related to capacitance, which is directly related to dielectric constant. This is the fundamental principle behind the capacitive sensor. So now if we move on to our circuit diagram here, bringing it back from the analogy to the real world, we can look at the circuit diagram and see how things are working. So our first and most important part is the timer circuit. This is just outputting a constant voltage for a constant amount of time, and then it comes back down to 0 volts for a certain amount of time and does that same thing over and over and over. In our analogy, this would be pouring a certain amount of water for a certain amount of time into a bucket. Then what we do is we look at the voltage that is stored across the interdigitated part of our capacitive sensor. And this is what just acts like a capacitor. And what we just learned was that the dielectric medium that's touching a capacitor directly influences its charge time based on the dielectric constant. So what we can do is look at the charging profile of the capacitor, and we can look at that voltage and see how much voltage did we get in this certain amount of time. So we can say, in our analogy terms, we poured this much water for this much time into the bucket. How full is this bucket relative to its maximum capacity? That's what we're looking at here, is when we apply a constant voltage across the capacitor, it stores a certain amount of energy, and we can then read that energy level as a voltage across the capacitor, or from the capacitor. So what we have then is a peak detector circuit. So what that does is it grabs the maximum voltage it sees, and that maximum voltage, again, tells us about the maximum capacity of our capacitor, which in bucket terms is how big is our bucket, which again is directly related to the dielectric constant of the material we're looking at that is touching the sensor. So that's how this works from a fundamental point of view. That's how we can determine the dielectric constant of anything that's touching this sensor. So here's some specs for it. If you're interested in that, its range is about 0 to 258. Dielectric constant is unitless since it's a ratio of permittivities, but we don't need to get into that right now. Here's a couple other specs, temperature, resolution, accuracy, if you're into that. But yeah, otherwise, we will be moving on to the next section, which is, why do we care? What's so cool about finding out the dielectric constant of something that's touching the Lunasat? Because we haven't really talked about that yet. And the most important lesson here is that dielectric constant tells us something about the composition of lunar soil that we're touching. And that's super important to our mission, because a lot of super cool things can be done if we have compositional data about what the soil or the regolith is made out of. And different elements and different combinations of materials in the lunar regolith will potentially cause a difference in dielectric reading. So that can be used as a way to measure composition. So, for example, we can look at Rainier Gamma. This is a lunar swirl, which is a magnetic anomaly, and the lunar regolith just looks weird there. Like, as you can see in the photo on the right, it's like way brighter than its surroundings. And the short story is scientists still have no idea why. This has been kind of an open question for a while. We say, why are there swirls? How do they develop? Why do they look different? So compositional data there, as you might imagine, is super, super important, because we can look and see if there's any meaningful composition differences between normal regolith and this really bright white regolith in a lunar swirl. And we can do that with our dielectric constant, which we can sense with a capacitive sensor. So that's kind of the science potential and value of this sensor. So now we're going to move on quickly to talk about analog signals and digital signals and how we can convert between them, because this is an important part of how we can actually get a reading from our sensor. So this is no longer about how the sensor fundamentally works, and this is about how do we take the reading that we get from the sensor and how do we represent it in a way that we can send to our computer and transmit from the moon and such. So let's talk about analog signals, and then we'll talk about digital signals, and then we'll talk about how we convert between them. We'll bring you through all of that. So analog signals are basically just a voltage level that has an infinite level of precision. So if you've taken some math, it means it can take any value in the real space. So that just basically means it has an infinite number of decimal points. So maybe we take a voltage measurement and we get 2.9846, et cetera, et cetera, et cetera, et cetera. Goes on forever. Infinite number of decimal places requires an infinite number or an infinite amount of memory to save. And unfortunately, our Lunasats don't have an infinite amount of memory. So we have to find some kind of way to lower the memory requirements of storing a value like this. So what we do is we turn it into a digital signal, which has a much more clipped amount of memory. So for example, what we do is we just divide our range of measurements into a certain number of bins, so to speak, and whatever bin our reading happens to fall in, we just output that bin number versus the actual reading itself, because the reading itself has an infinite number of decimal points. So if we say have a signal that varies from 0 to 1 volt, maybe we'll divide it into 4 bins. So we say 0 to 0.25 volts, that's bin 0, 0.25 to zero point 0.5 is bin 1, and so on. What that does is now we had an infinite number of values between 0 and 1, but now we just have 4. We can say if we get a reading of 2.98, et cetera, well then, actually that's out of our range. Sorry, using the other example. If we get a reading of, say, 0.60435, et cetera, well, we would say that's in the range of 0.5 to 0.75, so let's just say bin 2. So instead of outputting literally infinite number of decimal points, we can just put out one number, bin 2, and that tells us it's somewhere in this range of 0.5 to 0.75. So you might be wondering, well, how do we assign the number of bins? How do we get that? And that is actually based on the number of bits that we use. That's basically saying that's how much memory do we want to commit to saving this value. More memory means smaller bins, which means a better precision, so more precise signal. But of course, that comes at a cost of more memory. So what this determines is a bit is a binary digit, so it's either a 0 or a 1. So like the number 010 is 3 bits, and you can have like obviously more or less. And for each bit, it has 2 values, 0 or 1. So with a 3-bit number, we have 2 options for the first digit, 2 options for the second, 2 options for the third, multiply 2 times 2 times 2. That gives us 8 options, or 8 bins for a 3-bit number. So we'll bring you through an example real quick. We'll come up with a hypothetical sensor that has an output range of 0 to 3.3 volts, which is very common. And then let's say we want to commit 4 bits of memory to it in our microcontroller. That gives us 2 times 2 times 2 times 2, 16 bins. So 16 possible outputs for this 0 to 3.3 volt range. And if we divide that through, we see we get about 0.2 volts per bin. So let's say we get a reading and it comes out as 2.984, et cetera, goes on forever and ever. Well, we can look at that and just say, okay, that falls in bin 15. So now we went from an infinite number of decimals to just bin 15. So then the microcontroller will then just save whatever bin value that is and just output that. And then knowing the specifications, we can backtrack to find out it was in the range of 0.28, 2.8 to 3.09. So you'll see we do lose some precision, and that's kind of the nature of it, since more precision is more memory. So we have to make a trade-off between how much memory do we want to commit versus how much precision do we want. And more memory, of course, means that we have to have a stronger data connection all the way on the moon and commit more memory and have fewer other sensors able to store memory. So we always have to be making trade-offs of how much memory do we want to commit versus how precise of data do we want. So then on our next slide here, we can see how this looks in the real world, which I like looking at it visually. The blue line is an analog signal. And then if we feed that through an analog to digital converter, in this case, it has 3 bits, so 8 bins. You can see it kind of makes it more blocky and stepwise. And that consumes a lot less memory than storing infinitely precise values in the range of the signal. So you might be wondering, what's this all got to do with the capacitive sensor? Basically, this is how it works. This is how you can get a reading on your computer from the capacitive sensor. So what happens is, all in total, the capacitive sensor puts a timing wave out, puts a constant voltage across the capacitive sensor. The capacitor charges to a certain value, which depends on the dielectric constant of the material it's touching it. We take the peak value, that maximum voltage it reaches, and that's an analog signal that's related directly to the dielectric constant of the material we're looking at. We send that through the analog to digital converter, which then makes it readable to our Lunasat's microcontroller, which then it gets sent to your computer or gets sent to our Lunar Gateway, and then we get a readable reading that we can see on our computers. So all of that is going on every time you take a reading from our capacitive sensor. There's a lot going on there, but it's really great scientific tool that can help us look at the composition of the regolith and tell us a lot about what the history of the lunar surface might have been wherever we land.